Hi everybody, in this video we are working from the end of a packet here, starting at number 53, and we're working on, in this case, writing the equation of a piecewise function, but you're going to see a bunch of examples on this playlist regarding piecewise functions. We're going to be graphing them from the equation, we're going to be analyzing them, talking about limits, one-sided limits, f of evaluating a function at a certain point, what to do to make a piecewise function continuous, is a piecewise function continuous, and so on. But obviously if you're watching this in order, I'm telling all of you this at the end, but if you're seeing them as they upload, then you're getting it at the beginning. So yeah, so here we go. So we're going to graph, analyze, write, and more with piecewise functions. Piecewise functions are pieces of a lot of different functions working together to create one function. So you might have a situation where you need to model data or a situation with one function from one point in time until a certain other point in time, and then another function takes over and models the behavior from there on out, and another function from there on out. And that is probably a more realistic model. Not everything in, I don't want to say more realistic, because a lot of things in nature do follow quite interesting mathematical models, but this could be a realistic model depending on the situation. Anyhow, we're writing the equation here, and I've broken it up into three pieces. So we have the pink, the blue, and the green. So to write this, we're going to go in that order. So the picture I have up at the top of the screen, that one's sort of just pinned, so I can't write all over it. Like here, I'm going to be able to, write on top of it and whatnot. But the one on the top of the screen will remain untouched for now. Okay. So let's see what we got here. First one I'm going to look at is this pink one. Now, at first glance with this pink one, it kind of looks like a parabola, doesn't it? So let's see. What are we going up by? So it looks like we went up by 2, right? We went over by 1 and up 2. And then the next one from here, we went up 1, 2, 3, 4, 5, 6. Okay, looks interesting. So, so we should know, most of us, I hope, we should know what a pretty natural pattern is in a quadratic or a parabola. It tends to go as it goes out 1 unit, it goes up 1, it goes up 3, it goes up 5, 7, and so on, right? For further explanation on that, please go watch one of the videos on, where does the graph of the quadratic sort of come from and all that. Basically, I promise you the distance between the perfect squares is going to be consecutive odd integers, at least for regular x squared without anything done to it. Now, the one we have is going not up 1, but it's going up 2. It's not going up 3, but it's going up 6. So that's telling me that I have a vertical stretch by a factor of 2. So I hope everyone can see that. I'm also going to be writing this with the vertex placed right where it is, right over there, okay? And then I'm going to set my bounds from left to right. So let's get it started. So we said we have a vertical stretch of 2. We're shifted to the left 4. So inside of the function, right here, we're going to have x plus 4. That's inside of the house holding this x squared and making it a parabola. And then it moved down 3, so we can leave it like that. There's no reason why we need to change that into standard form or anything like that. This is perfectly fine. Now, comma is my way of saying when or under these conditions. So under what interval or what domain. So we're looking at this. It looks like it's from -infinity, comma, until the x value. It looks like it's stopping at the x value of -2. And being that it's an open point, I'm going to use a parenthesis, because that right there will exclude that value from being a part of the piecewise function. I'm also going to draw the curly little bracket there, and so far so good. So hopefully everyone else was able to get that same equation for that piece of the piecewise function as well. Now for the next piece. This is all very important that you're able to recognize the type of function that we're working with. So the next one I see here in blue is an absolute value. It looks like it went left 1 unit and then up 2 units. It looks like there was a vertical reflection causing it to face the way it's facing. but the slope of the sides looks like they're just still 1 and -1, so it doesn't look like I need to apply any vertical stretches, just a vertical reflection. So that means I will have the negative absolute value of x, so that now my house is not absolute value bars, but instead the house that the x is living in, it's not the parentheses squared, sorry, it is absolute value bars. So we went left 1, so that is going to be inside the backwards house as x plus 1. Went up 2, we're not in the backward house for that, so that is up 2, comma. Looks like they're closed points on both ends, so I'm going to use brackets, and that's going to go from -2 until +2. And there you go. There's the blue piece of our piecewise function. And then last we have the green piece. So for the green piece of it, it looks like we have, now you want to look because, you know, this could very well be a piece of a logarithmic graph. It could be a piece of a cubic. It could be a piece of a square root graph. So you want to analyze that pattern and kind of see, well, which model is this going to be? So we're going to go up 1 over 1. That's pretty standard for most of the graphs. But then it goes up 1 and over 3. So hopefully everyone knows what that is, and we're pretty familiar with that. And that would be the square root function, which is the inverse buddy, in a sense, to the parabola, right? I mean, technical restriction of domain, blah, blah. We'll talk about that soon. So we got our square root graph. It looks like there's no vertical stretches. It's not like we're going up 2 or up 3 while we're going over 1, 3, 5. So we're going up 1 each time. So it's pretty standard. So I have the square root, not the cube root. Cube root would be up 1 over 1, up 1 over 7, right? X, we went right 2. So now the house is the square root, all right? If you want to close the little end so you know where the thing's under the square root end, you could put a little tail at the end there. And then it went up 1 unit, comma, and that looks like with the parenthesis, that is from 2 until infinity. And that is it. That's all we got. All right. So that right there is an infinity and negative infinity always get a parenthesis. Parentheses for a number that you don't actually reach. You never actually can get there. You can just keep approaching it. Okay. So that right there is the equation of the piecewise function pictured. Any questions, comments, concerns, feedback, requests, leave it in the comment section down below. Hopefully you got that right and you're a genius. Some people find this very easy. Some people don't have any idea what's going on. I'm not going to lie to you. I didn't know what was going on. And frankly, when I was in high school, it's because I wasn't paying attention. So I promise you, if you put forth the effort, you will get it. It's just a matter of checking out if you're confused, okay? If you can graph transformations of parent functions as they are, then you can graph a piecewise function, okay? It's just a little mosaic, you know, you're just piecing it all together. So if you're happy and you know it, thumbs it up. Oh no, he got stuck behind picture. And if not so much, go ahead, thumbs down. My feelings won't be hurt. And look out for the next upload. All right? Bye for now. Adios.